better get you guys started here since it is past time, and there's quite a few concepts here and pictures, really, mental pictures I want you to grasp and get a hold of. Once we get through these mental pictures, then I think the rest of our electronics, although it gets a lot more sophisticated, if you will, falls right into place. And so I think, as I said last time after we went over the test, I think you will find this chapter the easiest chapter we've done so far this semester, by far, because it is very half conceptual, and then the other half is really some very straight mathematics. None of these long integrals of adding up a bunch of rings on a hemisphere to find the electric field, and none of that kind of thing. And so you'll see that in these next two chapters, and then we'll get into magnetism and have a lot more integrals to do then. All right, so certainly more of that to come here. But here's where we left off. I was trying to get you to conceptually see what is current and what is the resistance. Now maybe I should add to this what we've already covered. What is the voltage? That's not even part of the chapter, but as we put these three ideas together in just a second, we come up with the main point of this chapter, and that is, let you see Ohm's law. And it is exactly the same Ohm's law that we saw in lab, and many of you are seeing right now in your circuits class. For that matter, it will also lead to power and energy that is either being delivered or consumed in our circuit. So again, let's go back here and focus on what is current and what is resistance. And what I hope I got across to you last time was that the resistance you might think of as the stopping force, the part that is stopping these electrons from trying to flow. The analogy I did for you, and maybe worth doing it again, is to say, look at the flow of water. The flow of water is a lot like the flow of electrons, except we're a little bit more familiar with the flow of water. And so it's why it makes a good example. If I take this power supply, I turn it on, then the resistance is what is stopping the water from flowing. And there's a couple of factors that we will see in here, but one of the ones I was just trying to illustrate was, what if I just take this rubber hose and I kind of pinch it about halfway down? That little narrowing right there is adding resistance. It is stopping the water from flowing. And if I do it again, even less water flows. And so it makes sense that how much actually flows is connected then to this stopping force. And so we're going to look a little closer at this stopping force. What is this resistance? What are the four causes that are opposing these electrons from flowing? And that's what we will be discussing, that there are four. And so we'll look closer at that. And of course this is just really the amount of the flow we have. How much charge actually flows. And we left off then saying this, that if you were to take a wire here, and on a microscopic level, if you kind of looked here at a cross-sectional area A and said, okay, there are charges that are moving, and you started counting them. And not just how many, but how much charge. Now that's important because each charge may have the same or different amount of charges to it. And so I'm not saying how many of them flow, but I'm saying how much charge flows. So our current we defined was, what is the rate of which charge is flowing through? And so as you'll see here real quickly, is that this current then will depend not only on how many flow through there, but how fast are they flowing through, which I guess really comes down to also how many, but also how much charge each individual one has. Now, what I didn't get a chance to say, now that we are a little more sophisticated, is this should probably be written as an instantaneous rate. And so we will see our currents not as a change. Whoops, that's going to go on the whole time unless I turn it off. All right. The current then is a derivative, and we can of course do our calculus, meaning that not only do we have how much flows per time as the current, but the total amount that flows is then the sum of the current over time. We could add up how many of these charges begin to flow. And so we looked at this picture last time and we said, look, here's a good mental picture. If you have, in this case, some positives, and we've got positives here, and if this was a long wire, there would be more positives on down the road. But what's saying here is how many go by there every second? How many go through that little area? Oh, this I is for current. And so did I use I? Yeah, I used I. Yeah, so I is the traditional symbol. Oh.
How do you distinguish between that and the moment?
Oh, good point. We used I for moment of inertia. How do we distinguish? We don't. We do that to confuse students. No, I guess it's mechanical. So we use I when we're dealing with mechanical things. We use I when we do current things. Most of the time those don't overlap, but there's obviously the potential of some confusion. Yeah. So I know I don't have a good answer for that. We're just out of letters. Did I ever tell you guys the story at graduate school? I had this Russian instructor, and besides the heavy accent, and I was struggling to understand, he was zipping through all these symbols like crazy, and he jumps right into the Russian alphabet. He goes, oh, this is too confusing with using the same symbols. And so he starts using the Russian alphabet. And I was like, oh my gosh, I've never seen the Russian alphabet. And he's using all these crazy symbols, and it was driving me crazy, so I go, I'm just going to use the Greek alphabet. I know that well, da-da-da-da. Well, about 3 more weeks into the semester, he's finished the Russian alphabet and starts in on the Greek alphabet. It's like, oh no, I am in real trouble now. And so I had to go back just the whole day on Saturday and fix all my notes and change all these Greek symbols I've been using to his Russian symbols, only because he was starting to use the Greek ones. And so, no, he didn't do that. Fortunately, he had between I'll say English, but I guess it's Latin, isn't it? The uppercase, lowercase, the Greek, uppercase, lowercase, and the Russian Cyrillic? Yeah, and do they have upper and lower? Okay, and so by the time we got all through that, we made it through the semester, so we had enough symbols. So anyways, that's a long way of saying, forgive the symbolism, but yes, this is an I. If we do moment of inertia, I will overly emphasize that. But I don't think we do for a little while. When we get into magnetism, which involves current, then we get into motors, and we got to spin our motors, and we get into torque and moment of inertia. So I guess it is coming, and the potential's there. So, all right, but heading back to this here, this is the current I. It is listed as a derivative, and I didn't get a chance to say that. I did get a chance to say the units, though. What are the units to measure current? Amps. So what was the definition of an amp? Yeah, it's 1 coulomb per second. And I like to think of a coulomb as a bunch of electrons, 6.2 billion electrons every second. Now again, that's so many that I think you kind of lose the feel for how many electrons it is, and that's not real important. But what is real important is that even though we look at things like an amp and we say, oh, it's only 1 amp, it's 2 amps, it's 3 amps, when we do that, we can forget that what's really happening on a microscopic level, what is really going on is current is the flow of the charge. And that's what I wanted to emphasize by saying 1 amp is this many electrons every second. And I think that does drive it home. Now we had a second picture here to really emphasize that the challenge of working with any of our electrical stuff, and for that matter magnetic stuff, is that we don't just have one type of charge. And your author had a good picture of both positives and negatives. It was number 4, there it is down there, and said, remember that it's not just positives that can flow. In this picture here, B, he's got positives going this way. In my picture, I've got positives going to the right. And looking at this definition, I was trying to emphasize that this then would be the direction of the current. But not often do we have just positives moving. In fact, more often we have just negatives moving. Sometimes we also have both moving. But whether we have just positives, just negatives, or both, I wanted to make it clear, and I think I did, but it's one of the things that can lead to a big hang-up if you don't see it here at the beginning, is that negatives would go the other direction. And that's no different than what we've been doing before. We know if we took 2 plates, we charged one positive, one negative, and if we put a bunch of positives and negatives in between them, positives would go one direction and negatives would go the other. So nothing has really changed, except the movement of each of those charges contributes to the energy in the circuit. So the fact that one goes to the left and one goes to the right is not so important. And so what is important is that the charges move, and both of these contribute to the current. And so when a negative charge goes this direction, that means this side is less negative, and so dq dt is that way. So a negative moving that way means dq dt is that way. Does that make sense? And so the direction of the current is not defined as the direction that the particles move. And now I hope you see why we wouldn't even want that, because there are situations in liquids and gases like this where we have charges going in both directions, and both movements contribute to the energy, and we want to account for all of that. And so that's why we define it as the flow of charge, not the flow of particles. Very important distinction here, especially here at the beginning, because at the beginning we don't do too many situations like this, this, and this. We're always working with wires, and in wires we have electrons that move, and so we're always dealing with this scenario, and so it can drive you a little crazy for a while, saying, oh, the current's pointing that way, but the charges are moving that way. But I hope you see that with the negative sign there.
Can you explain why the current's pointing that way?
Again, let me try some numbers here. Let's, for the sake of conversation, say there was a small amount of charge here, plus 100. Okay? If a positive moved over to here, this would now go up by 1. Fair enough? So the increase is that direction. So a positive moving from here to here means dq that way. On the other hand, starting with a positive 100, what if a negative were to go this way? What's the charge here now? It's still 101, right? It is losing a negative charge. When it loses a negative charge, it becomes more positive again, right? So again, which way is the increase in charge? That way. The particle went this way, yes, but the increase in charge is that way. So the increase in charge will be in the opposite direction of the current, because the fact that it has a negative charge. And we'll see that in the math in just a second. We're going to go through the logic that Ohm went through and come up with Ohm's law. And you'll see when we're all said and done with this, we'll have an equation that says current equals, and it'll be an equation that has charge in it. And so if you put a negative in there, and it'll have velocity. So it'll have a negative and a velocity. So negative of the velocity for a negative charge means it's opposite.
What is the follow the positive charging used to be part of the assumption that only the positive charges move and not the negative charges? And if they found out the negative, they found out the electron actually has a negative charge?
I don't think you quite said that right. I think that Benjamin Franklin never assumed positives were moving as much as he did not know which ones were moving. And so he realized this scenario that it wouldn't matter. So I don't think he assumed that positives were moving and then he was wrong. I think he realized that you could have only positives. You could have only negatives. You could have both. He didn't know, and it wasn't until Hall did his famous Hall experiments that we actually found out it's the negatives that are moving. But Franklin just realized and said it doesn't matter, because if you're only interested in the change of charge, we can define that, and if negatives are moving, great. If positives are moving, great. If both are moving, great. It doesn't matter. Both of them would contribute. So not 100% on my history, but I think Franklin was smart enough to realize it doesn't matter. Although he was very curious which ones were moving, but he was unable to figure that out till the Hall experiment. Which, by the way, is a fun experiment. You guys will be doing it, but not for like 7 weeks. So we got to learn about magnetism before we do that. All right. Well, this is kind of where we left off. Let's continue then. And this will lead to the grand finale here of this chapter, which is Ohm's law. And here's what Ohm started with. He said, again, let's look at a microscopic level here. Let's take a small area of our wire here, or I should say small volume of our wire, and let's look a little closer at it. And he said, if you take this little volume, so here's the wire, and you go from one point to another, there would be a certain amount of charge in there. There would be a delta Q. Try that a little bit. But this delta Q, as he writes it, would be, what is the number of particles in there? And maybe I should say particles with charge times the charge per particle. All right? And so that's kind of his first step. And so in this picture, we're trying to represent it with these little brown little spheres here and say, okay, each of them have a charge of Q, and how many are in there? And in fact, we could break this down to write it as number of particles with charge per volume times the volume, of course, then times the charge per particle. And so he puts a couple of symbols here and says, all right, let's call this little n. Okay? And so you're going to see little n starting now and just a few times now, but more as we get into magnetism. And so the little n is saying, how many particles do you have per volume? So it's a density. Okay? How many are there per volume? The symbol for volume we've already been using quite a bit. It's a capital V, and let me make sure I put the little dash on top of there because I want to make sure that you see this as a volume, not as a velocity. Okay, and so there's a capital V. Now the charge per particle, that's what he's labeling up there as a Q. All right, and then he takes one more step here. He said, well, let's look at this volume. What's going to happen is these guys are going to move. And so if you're asking how much current flows through this little cross-sectional area, well, what you're saying here is in a small moment of time, delta t, these guys would move with a velocity v sub d. And so all of those charges would go through that area. And so we could write this volume as the area times the length. And of course, this length can be written as the speed that these particles are moving multiplied by the time. And maybe I should use the same symbols he's using there. So I think he uses a delta t for time. And so my first point and the first step that Coulomb did was to try to look at this on a microscopic level to get a better understanding. And ultimately we're going to come with Ohm's law that you saw in class. But I think going through the microscopic picture really helps your ability to solve problems, in the sense that as you start to work with them, you hopefully mentally see these charges, and they're moving in the wire. At least you see them mentally. Now what I have so far is this, that I would say the number of charges then that are going to move across this little surface is made out of a bunch of factors. The little n, which is the number of particles per charge, number of particles that have charge per volume, so that's the density of them. Then we've got times the area, then we've got times the velocity of them. The sub d, by the way, is going to be for drift velocity. More on that in a second here. And there's my charge of those particles. You see, if I divide that then by the delta t, this is a good way to kind of define the current. And this is what I was saying earlier. I said that we would come up with a little equation for current, and it would have velocity and charges in there. And so now maybe you can see a little bit better. I know this helps me to understand what's going on in my electronics by saying, look, what the current is are these moving charges. And it's really not just how fast they are. And it's not just how many are they. And it's not just how much charge do they have. It's all of those. You see, the current is what? How fast are they moving? How much charge does each one carry? What's their concentration? And all those together tell me what is the current. And as we'll see here, then that will, I think, help with our mental picture. And it helps, I think, with your math now. Now you begin to see it. If you put a positive charge and you multiply it by the velocity, then a positive times this velocity, these would be in the same direction. But if you take a negative charge and you multiply it by the velocity, you then hopefully see that the current is the negative of the velocity. And so again, we're seeing something like, and they don't really say what the charge is, but they do point out that the velocity is this way. And so if these are positive objects, then the current is this way, as well as the velocity is that way. But if they are negative objects, then I would have something that would list velocity in the positive direction multiplied by a negative number, which means then I would get current in the negative direction. So they don't say in this picture what they are. I think it's best then to kind of just think of them as positive charges that are moving, and then that way we can say, well, the direction they move and the direction of the current are the same, although that may not be the case. Now, I should give one more piece of information. You'll notice that we put a little d here. This V sub d is what we refer to as the drift speed of these particles. And maybe I should just be more specific and call them electrons, since if we're talking about a copper wire, as we often do, if I take a copper wire, then they are electrons that are moving. And I'm interested in their drift speed. Now, what do I mean by drift speed? Well, see if this picture helps a little bit. Because the electrons, and I'll do this one first, are already moving around in a wire. If I just pick up a wire right now and hold it in my hand, and if I could look on a microscopic level, wow, there's two of you with UCLA gear on and a Dodger gear. We got the first Dodger playoff game tonight and the UCLA-Utah game tonight. Oh, hey guys, I'm distracted here. Okay, so another LA, UCLA. Am I missing one? No? All right, you guys get an A. All right. All right. The wire, if you could look on a microscopic level, they would already be moving around. So to make it clear, we're trying to say that the current is not made up of just random motion. The current is made up of how quickly or slowly they may be moving or drifting through the wire. Here's what I mean by this. If this wire, if you could see on a microscopic level and you could follow one of the electrons, like this one here, it would move and maybe hit an atom, bounce off, hit another atom, bounce off, hit another one, bounce up there, hit another, bounce off here, hit another, bounce off there, and it eventually just kind of ends up back in the same place it started. So it's just randomly ricocheting around. And in that case, we would say the electron's not moving one way or the other. It's not having a net motion. Same thing with this one. This one, it bounces around, and after a couple collisions, it's really back where it started. And so I don't want to say this is the speed of these electrons, which, by the way, is enormously fast. The speed of these electrons is like 10 to the 6th meters per second. I mean, they're just ricochet around like crazy. But they don't have a net or a drift down the wire. Now, that changes if I hook it up. If I do this, and then the light bulb, and then this here, and plug it in here, and turn it on. Well, we only got 2 volts. But we do something like that. Now, my mental picture's a little different. My mental picture looks something like this. That although they're still moving very, very fast, they are having a push down the wire. And so in this case, here's the electron, and it bounces and bounces and bounces and bounces, and it's moving very fast in terms of its speed, but it is slowly migrating down the wire. That's the part that contributes to the current. And so that's the part we're talking about. What are their drift speeds? Now, their drift speeds are pretty small. I mean, they're in the neighborhood of about a centimeter per second, or often less, depending on, other factors here. 1/10 of a centimeter. You can see that the overall current is determined not just by their speed, but their charge and their area and their concentration. So we could say we have copper, and then we would know their electrons, and then we can get the wire size, and we could put maybe 1 amp through it or something and get some kind of calculation on what their drift speed is. But their drift speed is relatively small, But I'm not really worried about the number right now. I'm just trying to get you to see that there's really kind of two motions going on. There's a very fast random motion, but that doesn't contribute to the current. It's the drifting down the wire.
Is the Q referring only to one particle?
Yeah.
What if there's multiple kinds of particles?
Well, okay, then I guess this would be the summation of the concentration of one particle. I guess they'd be in the same wire. They would have different drift speeds and they would have different charges on them. Yeah. So, good point. Although, we'll wait till next year before we say, okay, what if we have, you know, positives and negatives and different types of positives and different types of negatives. But that's how I would treat it. Because again, the current is the overall flow of the charge. All right. Notice in here that it shows which direction is the electric field that is created by this power supply to push these electrons. That way. What direction do they drift? That way, right? And so the drift of the electrons is opposite to the field. But again, you already knew that, right? That is nothing more than our force equals charge times the electric field. So positives would go that way and contribute to current if positives were moving, and negatives would go that way. Well, let's keep going with this. Let's take what we have, and I'll get rid of this summation so that we only have one type of charge in here. But let me throw in one more word. How about a current density? And what I mean by that is how much current do you get per area? You see, I could have a situation back in this wire that maybe the wire changed its size. It went from a wide wire to a narrow wire. And so the amount of density could be different. And so it's just current divided by its area, which in this equation would mean simply this. J, the current density, would depend on three factors. We wouldn't have area contributing anymore. It would get factored out. And so we would have the concentration of particles, their drift speed, and the amount of charge each of them have. Now, why do I care about that? Well, this was kind of Ohm's first step. Ohm's first logic was to say, what is pushing these electrons? Well, it must be this power supply, right? He said, let's look a little closer at this power supply. This power supply has a positive and a negative. It's something like this. If I take my power supply, and I'll just put plus and minus like it's a big battery here, and I say, let's take a look at this wire, and I'll keep it fairly simple here, and since that it's just one wire, it's got the same thickness all the way through. And of course, we know that the electrons then would be moving this direction, so this would be the drift speed of them. If there were positives in here, they would be going that way. But again, if this is just a copper wire, we don't actually have positives. But we could still say the current is going that way, right? And so we have this wire with some current. And it was Ohm who started here and said, I wonder how much current density I have there. What would be pushing these? And he realized that what happens is this creates an electric field. And the electric field is throughout this wire, and that's what this picture is trying to show. It's trying to show that you have an electric field. Now maybe I better pause right there. Because a couple of chapters ago, we said there was no electric field inside a conductor. So is there or isn't there? Because I'm trying to say there is right now.
Because it was still.
Right. So remember our argument back, whatever chapter that was. I think it was Gauss's law. So.
The concept of field because it's something bigger than from.
Right. So we said that there was no electric field in a conductor after the charges moved around and reached equilibrium. Okay? And so I'm really saying the same thing now. What ends up happening is we come along with our power supply and we hook this up. And if this is at a higher voltage than this, voltage V, then there would be an electric field that is at least initially created that would be the voltage divided by the length of the wire. And I got that from our chapter 25, where we said, look, the definition of the voltage is the integral of the electric field. And so if the electric field is a constant throughout that wire, and so that's why I'm trying to make it simple, just a wire of all the same size has an electric field through here. Ohm said that there would be an electric field, and then the charges would start flowing. Now, at some point, maybe all the charges would reach equilibrium and there would be no electric field. But as long as this power supply still has charges, it is making an electric field. So I want to make sure that you don't miss what I said before, that the electric field is zero inside a conductor. But that's only once the charges have stopped moving. So as long as that light is on, as long as this thing still has electrons moving around through it, I would say there is an electric field inside that conductor. Now this one's plugged into the wall, so as long as it remains plugged in, it'll probably do this forever. But if this was a battery, you know what eventually would happen is the chemicals would run out, you would run out of charge, and then you would run out of an electric field. And then there would be no electric field in our conductor. So as long as the battery still has charges, then we would have a small electric field. And that would be an easy way to calculate it. What is the voltage, which in this case is 6, divided by the length of this wire, which might be about a half a meter. Yeah.
Is there an electric field radially outward of the wire as well? Or just inside the wire?
In this simple scenario, I would say no. Because to have it radially outward, I have to have a charge build up here, right? Those were kind of the problems we did in chapter 24 there, Gauss's law. And I don't think there's going to be a chance for charge to build up here, because what happens is the first electron comes out and it pushes on the next, 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 and then it goes into here. And so for every one charge that comes out, one goes in, and there's never a buildup of any charge in there. So I would say no in that case. Now I say that case because it could get a bit more complicated if I narrowed it a little bit. Then there would kind of be like a traffic jam and a buildup, and then I might argue that there's a negative charges building up on this side and then positive building up on that side. And then it would be a slightly different question. But again, in this very simple scenario, no radial one, just inside the wire and in the direction of the wire. All right? Well, as I said, here's Ohm's thinking. He said that there should be some current density. There should be some charges flowing. And he suspected that it would be related to this electric field. That how much current flows must be connected to how much it pushed. Now, unfortunately, he used the symbol sigma. And so your question earlier is perfect. You want to confuse symbols. Here it is. We've used sigma in the last couple of chapters. What did we use it for? Charge, surface, charge, density. That's not what he means here. Okay? And so we're going to use this symbol sigma, but only for a little bit. We'll get away from it because it can get confusing here. And so I'll use it here as the introduction, but what he really means by this is the proportionality constant. He does not mean a charge density. Hopefully I'll make that real clear. So maybe I should write it as proportionality constant, not surface charge density. Yeah, and I would agree, if we're going to keep it around, we should probably change its symbol. We're not going to keep it around, we're just going to use it in the derivation. So there's no point in giving it a different symbol as you were suggesting, because it's not going to be here for long. Okay? Once in a while it will come back, but for the most of the time you'll see we'll get rid of it. But let's give it an understanding. How about that? What would you use to describe this sigma? In other words, what if sigma was a big number versus a small number? Well, I guess if it was a big number, that means I'd get a lot of current, right? And if it's a small number, it would mean I'd get little current, right? And so Ohm calls it its conductivity and says, look, this is an indication of how well this material conducts. Some may do it better than others. We know that. We know silver and copper conduct really, really well. As far as the metals go, stainless steel, not so well. Nichrome, not so well. The plastics, the rubbers, the wood, those really bad in terms of conducting. Air, really bad in terms of conducting. So he calls this the conductivity of the material. Kind of makes sense. But again, I want to emphasize, do not refer to this as the surface charge density. That's not what he did. But the reason for that is right here. If you start with this equation right here and write current density is sigma, need a dry one, sigma times the electric field. So current density is sigma times the electric field. Then current density can be written as current divided by area. Electric field, as we already mentioned, can be written as the voltage divided by the length. If I rearrange this and put current by itself, I get maybe that. If I rearrange it one more time, maybe you'll see now what Ohm was after. Let me write it like this. And now, hopefully, we have some insight to what causes the current. A combination of the push and the stop. We are going to call this R for resistance. And we've already talked about that last time. You already saw it in the lab. What you didn't see is the cause of the R is made of the extra parameters. And I want to use this as a way of physically describing why we have resistance. I mean, yes, we have resistance. And then the next question is, why do we have resistance? And so what we have is Ohm's law here that says how much flows? Depends on how much push and how much stopping. Hopefully this isn't a surprise. Hopefully this looks a lot like what we saw in mechanics. What is the acceleration of an object? Depends on how much push and how much resistance, right? And so it fits the same thing in terms of our mechanics, just now we have electronics here. How much actually gets flowing here. And in fact, a very simple experiment of Ohm's law is what you guys did in the lab. You did something to this effect. You took a light bulb and, well, you actually had a resistor and you had a computer that could measure current and voltages. So you did it a little more sophisticated than this. But here's a good visual effect. What do you think would happen if I turned the push down? Less voltage. I only have about 1 volt here. Very little flow. I mean, so much. I can barely see it on. I'm suspecting at your distance you can't even tell that it is on. If I turn it up a little bit to maybe 2 volts, I get a little more push, which means a little more current, and maybe the light is just enough that you can see it. If I turn it up more, 3 volts, more push, 4, 5, 6, 7, 8, 9. I wonder how far this can go. 10, 18 volts. That's probably not good for it. All right. And so as I push it more, I get more and more current. But likewise, we can add some resistance in here. And so using the same one that I passed out last time, we have a long, 10 meter long, thin wire here. And so if I disconnect it here and maybe make a connection here and a connection here, now all of these electrons, this current has to go through this wire. Now in this case, it goes through the wire up to this point where contact is made to here. So if I move this down to here, it has to go almost the whole 10 meters. And that's going to add quite a bit of resistance, and you can see the light bulb is much dimmer than it was without the 10 meters of wire. Or I can slide this back a little bit. Did you see a change? Yeah. And now it only goes through about 5 meters of wire. And of course that would be less resistance and more flow, and it's a little brighter. If I keep going a little bit more, I can go, I guess, all the way back, and it essentially goes through none of this wire. It just goes right there, through there, and across there. And so that is the main point, eventually, of this chapter, is to get right here. Ohm's law. The amount of current depends on 2 factors. A, how much you're pushing it, voltage, which we've studied in great detail already. And then B, how much resistance do we have? And so let's study that resistance a little closer. You are hopefully seeing then that the resistance is made up of a bunch of factors in there. Let's look at those individually and see if they make sense to us. What I've come up with is that the resistance is the length divided by the area and also divided by its conductivity. And so when I look at this length, I'm not surprised that what is stopping these electrons from flowing is how long the wire is. I think I've illustrated that many times with this long wire and sliding it back and forth. I think this little picture kind of helps. Here is a wire. Obviously it's not a real wire, but it's our model of a wire. It has this much width and it has this much length, and the nails represent the atoms. Let's say these are copper atoms. If I were to take an electron and try to make an electron go through the wire, you can hopefully see that they encounter some resistance. I'm hoping you will see all 3 factors in here. This being the area, this being the material. And so as I keep moving this along, I think you could see that if this was longer, wouldn't it be harder for it to flow through a longer wire just because it's going to come across more atoms? Fair enough? I'm hoping also you will see that if the area of the wire is bigger, you would have less resistance. Or if the area of the wire is smaller, you would have more resistance. And again, maybe you can see that when I put a bunch of electrons on here. If I take a bunch of electrons, you can see that they start running into each other depending on how wide the wire is. If the wire is really wide, one can flow over here and one can flow over here, and they don't get in each other's way. You start narrowing it and they get in each other's way and they bunch up. So the second effect is, what is the diameter of that wire? And so those are two of the four reasons I want you to see how come these electrons are being stopped. What is stopping them from getting through?
Does the charge between the electrons themselves affect each other in the wire too?
Yeah, because that's really how they bump into each other. They don't really touch like these. They actually get close and then poof, push off each other because of their charge. Yeah.
Does that like make the resistance higher? Saying there's more electrons pushing on each other inside the wire while they're moving.
But I would say that has to do with concentration, and then that's where it comes back to area. So it's back to area, if that helps. And then the third factor is hopefully pretty obvious in here. This was the material. Remember when we started this, we said this is the conductivity of the material. And of course it makes sense. What if this number was a small number? Well, small number in the denominator means we're going to have larger resistance. So that number is a property of the material itself. And again, maybe you can see this in our little model by saying this would be where these atoms are. And so depending on the spacing of the atoms, and depending on how close they are and how they line up, they may flow through some materials better than others. And sure, they flow through copper different than aluminum, different than gold, different than stainless steel, and they all have a different conductivity to them. Yeah.
So far we've been dealing with electrons moving through solids. What about liquids and gases?
It would be the same idea, but we would now have the conductivity of our gases, our liquid. In fact, it's a homework problem that says in the upper atmosphere, there's a certain current density that NASA has measured, and a certain electric field that NASA has measured. What is the conductivity of the upper atmosphere? So it wouldn't change. You would still analyze this the same way. There are some more other interesting things that do happen, though. So it's not quite everything is the same. But at this point, it would be the same. And I better leave that alone there. Now, your author does one more step. Remember I said a few moments ago that we're not going to leave sigma here anyways. And so let's define a new variable. One that hopefully we won't worry with sigma. Unfortunately, it's rho. So even though I said we're going to get away from sigma, so you won't confuse it, we're going to introduce a rho. And we're going to leave that one so you can be confused. And the more you're confused, the harder it is, the more students that drop out, the less science and engineers there are, the more demand there is for people with the skill, and the higher my salary goes up. So there's one big evil plot in this whole thing is to make more money. That's what it all boils down to. No, but I do want to point out, again, that I'm going to use the symbol rho, and I do not mean the charge per volume here. Okay?
I'll just use a P.
I guess we could use P, but we're going to use that for power in a minute. So don't, yeah. And P has enough with power, pressure, momentum. Yeah. So, you know, maybe we said earlier we just need to go to the Russian alphabet here. Right? That's the whole. Huh?
Hank has 1,000 characters in it.
Okay, yeah. So, all right. But, yeah. All right. But since this rho is going to be defined as the reciprocal, and I think it works out nice because it is the Greek equivalent of well, that's not good. Anyways, it's just resistance here. But this is what we're going to call the resistivity. So in other words, the reciprocal of the conductivity is the resistivity. So if you've got a chance to read the chapter, and I hope you still are heeding to that good advice I gave you many times, long time ago. Read it before you come to class, and you'll have a better gist of where we're headed and what we're doing here. But your author writes it this way when he finally gets here and says, this is the equation for the resistance. And he tries to point out that there are 4 reasons, even though there are only 3 symbols up there, there are 4 reasons for the resistance. The first 3 are obvious. How long is it? How fat is the wire? What is the material made out of? There is one more that's not so obvious here. And our model doesn't really show it quite as well as I would like it to. But remember these atoms that are represented here by nails? Are they stationary? No. What are they doing? They're vibrating based upon their temperature. They're bouncing around. So if this object was really cold, then this would probably be a good model of it, because these nails don't move. And so this would be a picture of electrons trying to get through a wire that is cold. You might even say absolute zero at this point, because they're not moving. What do you think might happen if they started to move? Yeah, they would kind of be, the atom is bigger, if you will. And the chances of hitting it are much greater. And it's harder to get through these nails when they are moving around. And so buried in this little piece right here, in the material, is not just what is it made out of, copper, lead, silicon, whatever, but also buried in here is those atoms moving, and it's their temperature. And so we like to write it this way, that the resistivity is increased by a small amount based upon its temperature. And that adds to the, or puts the 4th term in here. And I thought I wrote this all down. I guess not here. But I do know that your author put the coefficient here, the alpha, in a nice little table and said the following. Table 1? No, that was the color code. So it must have been table 2 here at the beginning. And so this temperature coefficient, this alpha here, which I guess I should have put temperature coefficient. But that number there is saying that this resistivity would just be equal to that much at 20 degrees Celsius. And so scanning this chart, you'll see that the author lists what is the resistivity of a bunch of materials, and it says all values are measured at 20 degrees. And so some scientist was sitting in the lab, probably in Washington, D.C., there in the weights and measure, and said, let's measure the resistivity of copper. And they probably carefully controlled its temperature at 20 degrees and came up with that number. And so that is our resistivity at 20 degrees. But they also realized that it's going to be a little bit bigger when it warms up. And so maybe they warm it up to 21, 22, 23, 24, 25, who knows? But they do get it warmer, and then they can measure how much does it warm up, or how much does it increase by every degree. And so that's what this coefficient here is in front. And so you can see that as we look at this chart, the one at the top of the chart, silver, the resistivity is the lowest. And so if you wanted your current to flow really well and have very little resistance, you could do a couple of things. I mean, one of the obvious things is make it out of silver. The other three obvious things are lower its temperature, make the wire shorter in length, make it fatter in diameter. Those four factors will then change the resistance. Now, of course, silver gets very expensive, so not many wires are made out of silver. I grabbed this wire, and it would have been very expensive. It is made out of silver, so it is not. So what's right below it? Copper. And so fortunately, copper is relatively inexpensive, and it's high on that chart, and so nature's been nice to us to give us something that is cheap to get a hold of and conducts really well. And so, oh, great question. Hang on with that in just a second here. But like I said, this is made out of copper. And the reason I bring that up here is, notice this is a short wire. Now we have some longer wires because obviously there are times we want to connect things longer and longer. But the longer we make it, the more resistance. In fact, it reminds me of a couple of years ago when I was teaching this class. I had a student working down here at Home Depot, and they came out with this new, I was going to say pneumatic air gun, but it's not pneumatic. But it was a gun that shot nails. So it was a roofing nail, so it shoots the nails in there. But instead of being pneumatic and hooked up to the air pressure, it was a plug-in, and it used the current in the wire. And so to demo it and to put it out in front for customers, they put it at the front of the store. And in the front of the store, they put the gun, and then there was no plug, so they took an extension cord and they plugged it in, and they put the extension cord up in the rafters, and it went across the store, and after 100 feet, they plugged in another extension cord, and they plugged it across, and they eventually plugged it in. And they get out there, and I guess every customer who came in said, hey, let's try this. And it would shoot the nail about halfway in. And all the contractors would look at it and say, oh, what good is that? I'm going to shoot the nail halfway in. And so they shot it, threw it away, shot it, threw it away. Anyways, they were wrapping it up. They were going to send it back to the manufacturer and said, we don't want to carry this product, blah, 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 blah. Anyways, he was here in class, and we just did that. And he goes, oh, isn't that 200 feet of extension cord adding resistance? So the next day he goes back and he takes it and he undoes it, and there's a plug off to the side, and he takes about a 20-foot extension cord, and he got one of the high gauge ones, one with the big fat. So if you go there, you'll see you can buy extension cords. The real thin ones are 14 gauge and 16 gauge, then they go 14 gauge, and unfortunately the number gets smaller as they get thicker. So he gets a 12 gauge 20-foot extension cord, comes out, shoots it in, shoots the nail all the way down. It was a great story. And he's all, yeah, I came back. We sold 100 of them today. Everybody who came in loved them. And they were just shooting the nails in left to right. They don't have to get out their compressor. So made a big difference in the extension cord. And in that case, they wanted to get as much current as possible. And the difference in the resistance from that extension cord really, really mattered. Now, back to your story, you noticed, yes, notice copper is a better conductor than gold.
Back to that equation, is rho not just the material itself without the temperature?
Right. Well, it is It is its resistance at 20 degrees. Or whatever your chart labels, but our chart labels it at 20. So 20 is a nice number to work with because that's roughly what we would be doing in the lab. And so if you have a problem that says calculate how much current, that means you're going to have to figure out how much resistance. In order to figure out how much resistance, you need to know these three factors. And so you're going to open up your book, you're going to look at this chart, and you're going to look up copper or aluminum or whatever the material is and look up the resistivity. Now, if they tell you the temperature, then what they want you to do is to factor in a higher or lower temperature to find out the resistance. In fact, going back to last week's lab, we purposely did the light bulb and measured its resistance when it was cold. Do you remember that one? And then we measured the resistance when it was hot. And if I remember right, you got a resistance of about 60 ohms when that thing was hot, and something more around 15 ohms when it was cold. And clearly a change in its resistance. And that's what you're seeing here. And we use the light bulb because light bulbs, we change its temperature by a lot, about 2,000 degrees. And so you can see a dramatic change in the resistance of our light bulbs. Whereas if you look carefully at this number, if you are just getting the resistance on a cold day versus a hot day, and maybe the change is 10 degrees Celsius or even 20 degrees Celsius, look how small that coefficient is. It's just not going to change it by much. And so a couple of degrees here and there, we don't worry about that. But 2,000 degrees, yes, we do measure it, and that was the point of the lab. Yeah.
What makes like supercomputers so sensitive to changing them? Why they have such influences?
Great question. Hang on for that. Just a few more minutes. How are we doing on time? Oh, we're great on time. Yeah, great question. Now I want to come back to your question. Your question said is notice this, because notice that copper is a better than conductor than gold, or even platinum. Is platinum up there? Yeah, and platinum. And yet I bet many of you question that because you go to the electronics store and you buy your gold or platinum tip connectors, right? And you go, ooh, let's hook up my audio video equipment and let's pay extra here for these platinum and gold covered connectors. Why?
They're rare.
Well, you pay extra because they're rare, but why would you put them on? Why would you put gold on the connector here? Did you notice this is not copper?
To prevent
Right. So although copper and silver are great conductors, they also react with oxygen very easily. They oxidize. So, whereas my whole inside piece of wire may be made out of copper, if I have a copper connection on here, it won't be copper for very long. It will become copper oxide. And copper oxide does not conduct well at all. So, the idea is to make the whole wire out of copper, but on the surface where the connectors are, use a metal that won't oxidize. So this is just stainless steel. It's about the cheapest you can get of having something that doesn't oxide on it. But we could make platinum or gold on our tips, and then we would have something that doesn't oxide and still has a good conductivity. So to keep the good conductivity, we like to put the gold and the platinum only on the connectors, only on the tip of it, and then the rest of the wire is still made out of copper. So that's why I think people naturally think that gold is somehow a better conductor, but it's not, as you can see there in the chart. Well, again, let's keep working with this model, but I did want to pause here for quite a long time because I think this sets the stage for really the next few chapters of why do we have resistance. The main equation is going to be right here, Ohm's law. That how much current you get depends on how much push and how much resistance you have. The push, as we are seeing, the stop it comes from 4 factors. And you also saw that the current comes from 4 factors. The concentration, the velocity, the area, and I said velocity. Uh-oh. What were the 4 factors? made our current? Oh, the charge. Yeah, duh, I'm missing the charge. Okay, so the charge, the velocity, the area, and the density of them. And that's the point of this chapter, to give you this microscopic view of what is going on down underneath Ohm's law. Because what the truth is, once we start hooking it up, we won't really be too concerned about whether the resistance is caused because the wire is long or the wire is thin. We just have some resistance. And when we hook it up to our power supply, we will take that voltage and divide it by that resistance to figure out how much current we get, and not really pay too much attention on the microscopic level where it came from. And this, like I said, kind of helps us with that understanding. I'll keep going here. In fact, I'll go back to a picture of these things moving on a microscopic scale. But before I leave this table, I want you to notice one other factor as you scan down. See all these materials? All these materials mean their resistance changes with temperature, right? The fact that they are positive numbers tells me that the resistance gets bigger. What do you notice about the carbon, germanium, and silicon? They have a negative coefficient. What would that mean? Yeah, as they get hotter, they actually have less resistance. How is that possible? Well, let's keep going. And so, keep working with Ohm on a microscopic level, and coming back to this picture of them kind of drifting as we apply a force. Ohm continues on his work and says, all right, these electrons, as they are flowing through the wire, may look something like this. Here's that electron. Now remember, this wire is hooked to a battery. Oh, let me get it the same direction I have there. Okay. And so when I hook up this battery, there'll be an electric field this way, which means they will be flowing like that. But it'll be a bit more complicated than that. Because wouldn't this movement from, say, here to here before it makes another collision have a force on it? And a force means it accelerates during that time. Now, it eventually accelerates and hits that one and then loses all that speed. Ricochets and gains some more speed. Ricochets and ricochets. But during the time between ricochets, isn't it being pushed and isn't it then accelerating? So what we really mean here by drift speed is a bit more complicated. It's kind of the average speed. And so here's some more work by Ohm. He said, look, let's take Newton's second law that says this would describe the acceleration of these electrons. Now, the force on the electron would be the charge times their electric field. If we also remember from Physics 121, our mechanics, this would kind of be a description of the speed of them. Now, in all fairness, that is only true for constant acceleration, right? And this doesn't really have constant. It kind of does. Like between ricochets it does. Between ricochets it would have a constant force. But then when it makes a ricochet, it's going to be a huge force and a huge acceleration. So why don't we do this? Why don't I say, what is kind of the average speed? And I think you're familiar with that symbol, aren't you? The little bar over top? Yes? No? Okay. So the average speed. And so what I would really mean is this would be the average of those factors. Now, the reason I say that is because we could break this down into its average initial speed and its average acceleration multiplied by time. Now, let me start with its average speed. Again, more conceptual than mathematical, but if you kind of mentally picture these things ricocheting, every time they ricochet, they may ricochet and go forward, they may ricochet and go backwards, they may ricochet and go up, they may ricochet and go down. And after the ricochet, then they start accelerating again. So after each ricochet, I'm going to take a hunch that the average initial speed is 0. Fair enough? I'm not saying everyone is there, but remember there's billions and billions of these things, and even that's an understatement of how many electrons there are. And so, looking on this on a microscopic level, I could probably guess that, okay, some are going to go up, some are going to go down, some are going to go left, some are going to go right. On a statistical average, they're going to be 0. So, you can think of this as after the ricochet, they stop. Of course, the truth is they don't stop. But on average, they would be stopping. All right. Then let's look at the other side of the equation. So average speed would be the acceleration times the time. Well, we just said what the acceleration would be on average between them. And so this would be QE over M. And then maybe I'll just write that as average time will give me my average speed. Well, this is a good time to use yet another symbol, tau. So that what I mean by average speed is what? Well, it's really connected to how much time is between them. Now, agreed that not every single collision has the same amount of time between them. But what this is saying is your average speed is connected to the average time it has between collisions. And so this tau is really a mathematical way of saying what is the time interval on average between collisions. So again, just if I'm getting this straight, I want you just to kind of have this conceptual feel that, again, the mental picture is there are billions and billions of electrons ricocheting around here. But they hit. Some go up, some go down. On average, they all start with 0 speed. Then, as they go away from the other atom, some are going to hit the next atom right away. But others may go hundreds of atoms before they hit the next one. So there's some average amount of time. And so I'm not saying everyone has this collision time. But what I'm saying is this would be an average. Because this then would be what I mean by the drift velocity. The drift velocity is the average of all of these interactions. Now, a few moments ago, maybe more like a half hour ago, we had this equation on the board. Whoops, yeah. Where the current density was related to that drift speed. We also started this whole discussion with this, which I suppose now we can write as this. If I put these together with what I just did here, let's see what we get here. If I take this and say J equals, and I put N and Q, and then I replace it with drift velocity of Q E over M tau, I lost myself here. Oh, so that would be the substitution of that one into this one. And if you rearrange it, n q squared tau over m e, I hope you're seeing that we can even get further insight to this idea of resistivity. The resistivity is made out of many factors itself. And so, like I said, the point of this chapter is really getting Ohm's law, but also understanding it down on a microscopic level. We're seeing where the current comes from. We're seeing where the resistance comes from. And remember, one of the factors of the resistance is the resistivity. And now, to kind of get close to the end of the chapter here, we are seeing what causes the resistivity of the material. And I think it begins to make sense. You look at different materials, and I'll call that table 2 back up here. You look at things like silver and copper, and you say their resistivity is really low. You begin to say, why is it really low? Well, what's nice about silver and copper is down here, the amount of collision time between the two atoms is really long. These electrons can go hundreds of atoms before they hit the next one. And because this number is big, the resistance is small. But another reason for silver and copper is you have a large N. What was this N again? We started the lecture. It's what? It's the particle density, right? And there is lots of electrons per volume in silver and copper. And so they take a lot of these really, really well. Yeah.
Is tau dependent on the size of the atom? Wait, no.
In part. If I start getting too much detail smaller than this, we have to go, and you haven't had 123 yet, but we have to get in what's called quantum mechanics, and we have to start looking at these electrons not as particles but as waves. And so I'll say kind of yes to that, but now you're looking at subatomic features, and we need to teach you one more thing of quantum mechanics before we can teach it. All right. But here's what I wanted you to see. Remember when I got rid of this chart, I said there were positive and negative numbers. Let's just look at the positive numbers for a moment. These metals up here, or whether they be aluminum or gold or iron or silver or copper, what happens as you begin to heat them up, and as those atoms start moving faster and faster and faster, the chances of an electron getting hit are greater and greater and greater. And so the time between collisions goes down, 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 down. So what happens to the resistivity? It goes up and up and up. This number here doesn't really change. This is how many charge carriers do you get per volume. And if it's silver and copper, every atom, when you put it together in a solid, loses about 1 electron. It doesn't matter what its temperature is. But here's the neat thing about the semiconductors. The semiconductors, as you heat them up, and as those atoms move faster and faster, they still get in the way of the electrons. This number here goes down, down, down. But this number goes up, up, up. Because in our semiconductors, when you put a bunch of carbon atoms together, only a few of the electrons come away from the carbon atom. Not many. If you heat them up and they start bouncing around and hitting each other harder, guess what happens to a few of those electrons? They come off. And so some materials this number can actually begin to increase, and you get more charge carriers as they slam into each other. And that's what happens in this area of your semiconductors, your carbon, your germanium, and your silicon. So even though you still have the atoms shaking around and getting in the way more and more and more, and so this number is getting smaller and smaller, this number is getting bigger. And the net effect is that for some materials, and really it's the materials that this number was never very big to begin with, but the ones that were not releasing all of their electrons in the first place now start to release them as the temperatures go up, and now they can actually become better conductors. And so silicon in particular is interesting because the world around us is built on silicon. And silicon, when you heat it up, actually conducts better. It is a huge trouble for electronics because what happens in a normal wire is what we call self-correcting. What if I were to take a light bulb when it is cold? Well, its resistance would be low, right? So when I first turn this on, there is 8 volts divided by a small resistance. That's going to give me a lot of current. But as it warms up in that first fraction of a second, and as this light bulb is warming up and its resistance increases, as you saw in the lab, going from about a 15 to a 60, so this has 4 times more resistance, what would that do to the current in here? It would decrease it by a factor of 4. And as that resistance increases, as the current decreases, then that kind of keeps the light bulb from getting hotter and hotter and hotter. What if it was the other way around? What if as this light bulb got hotter and hotter, the resistance went down? Right, I would first turn it on, I would get quite a bit of current, then the resistance would go down and I would get even more. And it would get even hotter, and it got even hotter, what would happen? It would have less resistance and it would get hotter still. And if it got hotter, less resistance, more current, hotter still. And this would just keep continuing to get hotter and hotter until the whole thing finally catches on fire or smokes or breaks or something. And we refer to this as thermal runaway. And so there's no self-correcting like a light bulb when it comes to silicon. And so when you have something made out of silicon, when you have all these great microprocessors that are in your phone and your computer and your iPads, and something goes wrong, it goes dramatically wrong. It doesn't self-correct and say, oh, a little hiccup, a little extra current, no big. Oh, no, it's a little extra current gets hot, then a little more current gets hotter, a little more current, and pretty soon the thing doesn't work anymore. And the thing, a little smoke comes out the side and you go, it's broken. And so working with silicon has its challenges, and that's a big one, unfortunately, that we don't have the self-correcting. Now, yeah. Again, not an easy answer to give you until we get more into our quantum mechanics, but I will try with a non-quantum mechanical answer first, and then if you're good with that, then I'll go all forward. But remember, if I have, say, one material, let's say this is silver, and so I've got atoms of silver that look like this, but I have a different material a little bit lower on this chart, let's say iron, and it looks like this. And so each of these little plus signs, I'm trying to represent where the atoms are in their lattice. If I send an electron through one and compare it through an electron to the other, you can kind of see how this off-spacing makes it so that if this electron missed this first one, uh-oh, it's that one. But this one, missed, and so things like this, silver and copper, by their lattice structure and how they interact with the atoms, could be very different than iron. And so their lattice, their charge, how they're arranged can be very different. Good, you're good with that one? So I can stay away from quantum mechanics, good. and so that's kind of a first level explanation of it. But it also leads right into, and I'm glad you asked it because somebody else asked one, what about superconductors? You ever heard the phrase superconductors? Do you know what a superconductor is? Yeah, and so interesting enough, there are materials under certain circumstances, what we call superconductors. They're not just conductors. Oh no, they're super. And why do we call them superconductors? Yeah, the resistivity is what? 0. There are actually, in rare cases, materials that the electron will never hit the atom as it moves through. In other words, what is the time between collisions?
0.
Infinity, right? What is 1 over infinity? 0, right? Its resistivity is 0. It never hits an atom. Now, this is a rare case. Let's draw some pictures. Let's extend on this picture that we got started here. Yeah.
Are carbon nanotubes and graphene superconductors?
No. No. Those are not superconductors. No.
How do you get electric field in space though? Doesn't hit an atom, that means there's nothing around.
No, there is.
How's that?
They're just cooled down material. It's not.
So let's take a wire again. And let me draw the lattice here. And so I'll just make maybe something like this. And in this lattice, this seems to be a good shape that an electron may actually never hit one. You may take an electron right here, and if you send it between two atoms, maybe it'll never hit. Now, unfortunately, the chances of that are really, really slim. Because even if you could start perfectly in the middle, isn't this electron attracted to the positive? So this is like saying, can you balance a pencil on its sharp point? And I guess you might say, well, in theory I could do it, but you're never going to get that pencil to balance on a point. It's just got to be perfect for that to happen. And you're never going to get it perfect. What's going to end up happening is something is going to be off a little bit. Maybe this atom will be off, and that will attract it in, and it'll start it on a different path, and eventually it's going to hit an atom. So the chances of having a superconductor are really, really slim, yet we can still have them. And so let me keep building on this.
What if you like move the electron so fast that it like I don't know, like it escapes the
Yeah, what happens if you put an anion? This is like a fuel.
Not sure I'm following your question.
Okay, like what if you move the electron so fast that it like you know how it like it's attracted to the positives through like
Yeah, the positives and negatives are attracted.
so you move it so fast so that it like escape velocity of the
Well, it already is escape velocity, right? Remember, this electron actually started with my copper atom when I had one copper atom, and then when I put it together, they escaped. And so they're kind of floating around in there. Now they're getting pushed by this electric field. Now, before I kind of lose this mental picture, maybe I want to keep going back to this drawing here. So what I'm really saying here is something like this, I will probably never have of a superconductor. And in fact, you could imagine that as the temperature got higher, the chances of getting a superconductor are even less. So as we'll see in the next chart, you're only going to have superconductivity below a certain temperature. Because above a certain temperature, these atoms are moving so much that even if you kind of got it started right, the movement of them gets them out of place, and these electrons are eventually going to hit. And in fact, it's not just that you have to have a low temperature. The other effect is you have to buddy them up. And I'll only draw a couple on here so you begin to see. But when you have both a low temperature and a buddy system, they can work. Watch. This first electron, as it starts to go through here, is not only being attracted to this positive charge down there, but it's being repelled by that one. And the same thing can be said all the way through here. And so if we have what you might call an array of electrons, a buddy system of an electrons, grouping together, they can actually kind of set themselves so that they go through. There could always be imperfections due to small temperature, not big temperature, but small temperatures, that these atoms may move and cause these to come out of alignment, but then the other ones would react to that, and you would have kind of a self-correcting process all the way through, and they never hit. So superconductivity is quite possible, but it's very, very sensitive to the temperature, which I think was your question earlier on. It says, why are the superconductors so temperature sensitive? And that's why. It knocks them out of place, and at some point they don't even become superconductors. And so that's why your author gave you, I think this is table 3, that he lists some of these different materials, and some of the simple ones. I think mercury was the first one discovered here. Oh, and I think they have some good data here in your graph, but this was more of an accidental discovery. This was a professor and a graduate student, and the professor said, you know, let's keep cooling our mercury lower and lower and lower, and let's find its resistance at lower and lower and lower. And the graduate student got down to about 4 Kelvin, and then said, oh, the resistance went away. And the graduate student went to the professor and said, it's gone. And the professor said, yeah, right, sure. I don't know what you did wrong. It's probably your partner's fault. Try something else, you know. And they tried it again, and they tried it again, and they tried it again. And so it was one of these amazing discoveries that was like, well, where did this come from? Nobody expected this. And so they tried it with a bunch of other ones here. And so you can see these do get superconducting at low, low, low temperatures. Now in recent years, and this is kind of the big push in science and engineering, is could this happen at higher and higher temperatures? I mean, a good example of this right now, as electricity is being generated in this country, half of that power is lost to heat in the resistance of the wires as it is transmitted from the power plant to the city. And half, almost half. It's an amazing amount of loss of electricity. So, what if we didn't lose all that half?
We need a superconductor.
Right, and if we had superconducting wires strung out across this, we would use half as much oil or natural gas or coal, whatever it is that power plant is using to make the electricity, just from that alone. And plus, we would have other issues go away, like what is one of the biggest challenge of making our electronics smaller and smaller and smaller? The heat gets more concentrated. And so as we get smaller, that heat does an enormous amount of problems. You've got to get the heat out of your processors, and it's a challenge. And those of you who've ever opened up your computer will see that. There's usually a cooling fan bringing air into the computer. Then there's usually a fan built on the processor itself, and some of your fancier ones then have a liquid-cooled system. And so they run liquids through the processor to keep it cool. But it's a huge challenge and a huge limit in our technology of the heat. And that would all go away with superconductors. And so in recent decades here, some of these crazy mixture of elements here, which, interesting enough, what is that? Mercury, barium, calcium. Is that a carbate? Copper. Oh, it's copper. Copper oxide, which, by the way, at room temperature wouldn't even conduct electricity. It would be a ceramic. Becomes a superconductor below 134 degrees, or 34 Kelvin. I guess I can't say degrees, but 134 Kelvin. And now, maybe by disclaimer, I should emphasize that this little model that I gave you of superconductivity right here is a good explanation of what's going on for our elements. We start to get to these, and nobody really knows. They work because an experimentalist went into the lab, mixed the chemicals together, tried it, and cooled it down, and got superconductivity, and then you go ask why it happens, and I don't know. But that's your job. And guaranteed Nobel Prize here if you can figure out why these things are superconductivity. And if you could, that'll probably open the door to higher temperatures, because once we understand, then we can begin to build things with that understanding of how they work here. And so if you want a quick couple of $1 million, just figure that out and you'll get a Nobel Prize. You'll probably already have a few million before you even get the Nobel Prize for that. But you can sell it around the world. Now you'll make billions, and you'll remember City College, and you'll donate so we can get a new ceiling and new paint on our walls and maybe a bigger building, and your professor loves his Ferraris red. Okay? So that's kind of where science is right now in terms of technology. And so we don't do much with superconductivity yet, but there's certainly a lot of great talk. They carry lots of current without heat. Using it to elevate trains is a big push right now, and getting lots of current, lift up the train so the train doesn't have the friction with the wheels going along the bottom, and just frictionless train, although it's still got air friction. So I don't know, maybe we need to build a tunnel and make a vacuum and just hope it doesn't open up and everybody inside of the train dies. But it's just, but once we get started, we get a nice little idea there. Well, one last thing. Oh, here's the surprising data that I was talking about, and just kind of dropped off right at about 4 Kelvin. Just boom. Where did all the resistance go? And kind of the first discovery. Well, one more thing, and then we'll get into some example problems if we will have time, and if not, we'll get on Tuesday and then go on to the next one here. But now that I think we've got, I hope so, this was the whole point, a good microscopic view of what is going on, that the resistivity and the reasons we have a resistivity, and then the resistivity, the length, the temperature, the area, that gives us our resistance. And you put all that together, you get Ohm's law. Let's actually then hook up something as simple, and I'll just disconnect this again and just say, all right, what if I just did this? Power supply, resistor, wires, light goes on. How much power? So if I were to draw a picture, I guess I would do something like this. There's my voltage, 8 volts. Now I'll just talk in general, so I'm just going to call that V. There's my voltage of my power supply. Mine happens to be set at 8 volts. If I then take a wire and I hook it across and I go to a little thin wire, which for the first time in this class, I am going to change the symbol and give you our 4th symbol. And I think our 4 out of 5 before we finish the semester, we've seen the symbol for capacitors, we've seen the symbol for voltage supplies, we've seen the symbols for switches, and now the symbol for resistors. And so we draw a little squiggly line here, like the electrons have to make this tight turn, and they're kind of being resisted as they go through. They're having troubles to get through here. That's what I have here. I've got a power supply, and I have a resistor. All right? if I were to look at this and maybe kind of imagine myself in the wire at point A, and for a visual discussion, I might say, what is the potential at different points in this wire starting at point A? Well, I'll call that my reference point. So I'll say there's 0. But the whole point of having a power supply is that as I imagine myself moving through this power supply, which I know it sounds kind of funny, but ever watched the Magic School Bus when you were little? Yeah, great show. If you got some time, go back and watch it. I mean, and this is one of my favorite ones, where the Magic School Bus gets small and they go in the wires and they go through the battery and the voltage increases and then they go through the little resistor of the light bulb. And okay, but it's a great one. Not as good as the food fight one, where they argue about whether it's violet or purple. Now that's a really good one. But all right, but this is a good one too, where the little school bus gets down. That's kind of what I'm saying here. Imagine yourself in the Magic School Bus, all right, and we shrink down and we're going through this little school bus, and as we go through here, we would increase our voltage. And in this case, it's 8 volts. Again, let me just talk in general and say it's V. So the voltage there increases. Now, if this mentally helps, think of this back as our water analogy. This is the pump. I went from one side of the pump to the other. And as I move through the pump, I have gained energy. And so there's a lot of energy. The water slide helps me here. This might be a pump that lifts water to the top of the water slide. The water actually gains energy. And I think because we don't see something get higher, it's kind of easy to forget that we're talking about energy, but it's easy to visualize potential energy. This water goes up a pump, and it's now it's the top of the water slide. And of course, now the water is going to go down the water slide and go back up, and down the water slide and back up. And so this is our flow of current in here. Yeah.
Isn't the battery more like a capacitor, really?
Where are you going with that? I don't.
Wait, you're talking about the flow of charge or the flow of electrons?
No, I'm not talking about the flow of anything. I'm just looking at the energy. So again, if you just imagine yourself walking, not the electrons moving, you inside it, you move. If again, this is water, up a pipe. If you could freeze the water in time, I'm not talking about the movement of the water, but if you could get in the pipe and go up the pipe, you would gain energy. You would be at a higher point and you would have more energy. And so that's what I'm trying to draw here. That point B is at a higher energy than A. And as I move from point B to point C, there would be a change in voltage according to Ohm's law. And so now we need to ask this question. How much resistance is there from point A to B? Well, we just spent a long discussion saying the resistance is the resistivity of the material, and I'm using copper, length divided by area. So in my little model here is what I'm talking about, this wire right there. And there's not much resistance in there. Oh, is there some? Oh yeah. A fraction of an ohm. It's made out of copper. It's fairly thick. It's not very long. And so, although it's not completely accurate, it is pretty close to saying the resistance is 0. And certainly compared to that light bulb. Remember, that light bulb was on, we measured about 60 ohms. And so I'm comparing maybe about 100th or 1,000th of an ohm here compared to 60. And so I'm just going to say, no resistance. Not completely true, but compared to the other part of this circuit, it is true. So we will say that there is no change in energy if there is no resistance, and there's no resistance if we have good, thick, short wires. Okay? And so that's what I part of this whole discussion. And so I get to point C. Now, as I go from C to D, then I go through the resistor. Now, in that case, there is a change in voltage. This was our whole discussion about Ohm's law. And the resistance depends on the material, the length, and the area. Now, in this case, the material's tungsten. It's not very long, but it is really, really thin. And it is really, really hot right now. And so, of course, that's why I get about 60 ohms right now. So I can't ignore that resistance. So is there a change in energy? Yes. And so the energy goes somewhere. And in this case, the electrons are going through. They're hitting the atoms because of resistance. So what happens to the resistor? Gets hot. Exactly. I'm hitting those atoms. I am making them go faster. Where does that energy go? It goes into heat. And so all these electrons turn into heat. If you like the analogy of this water went up to the top of the water slide. Then at the top, it really didn't change its energy. There's a big pool where the water just kind of floats and kind of moves around up at top, and that's where people get in and get on the raft. Before now, they get at the end of the water slide, and now they go down the water slide. And that's what's happening here. The water is going down. The current is losing its energy. And as the water comes down, it hits and bounces around, and the water begins to warm. And so the water gets down, and as it gets down into the bottom pool, it has lost all of its energy. Where has it gone? Into heat. And so the pool down at the bottom is a little bit warmer than the pool up at the top. In fact, it reminds me of a historical argument when early scientists said that. And somebody said, that's not true. That means it would be warmer in the bottom of a waterfall than the top. So they were in New York, so they went to Niagara Falls. They put a thermometer at the top, they hiked to the bottom, they put the thermometer at the bottom, they said, oh my gosh, it's 1.5 degrees warmer at the bottom than at the top. And hence heat became energy, and the whole world changed because we realized finally what heat is, and it's the movement of these molecules. And until that's what would happen here. And no doubt you've touched a light bulb before. It is hot, and all that energy is converted to heat. And so in this case, what would happen is it would go down in energy. Now, a real key factor is asking how much did it go down? But if this right here is thought again as having no resistance, so this last part of this wire right here, from D to A, has no resistance, then there would be no more voltage change. And so the water would come all the way down, and then it would just kind of float around in the pool at the same level until it got sucked up the pipe again and got. So we gain energy here. We don't really change any energy as we move the water to the edge of the water slide. We then convert that potential energy into a heat energy as we come down the water slide, and then we just kind of float around and then back up. And so there's kind of our water analogy to what's going on in this circuit. So if we go to calculate the change in energy here, this would be the amount of charge times the change in voltage. And part of the reason I went through all this is because the change in voltage is the 8 volts. It gained this much, and then it must lose that much. Again, like the water park, if the water goes up to the top where the water slide is, if it goes up 100 feet, how much does it come down? 100 feet. Can it come down 75 feet? It can't get back to the pump until it goes all 100 feet down, right? Now, it may go 75 and then into a pool and then down another 25. I certainly could do that. So we could have something that instead of looking like this, may look like this and then like that. Sure. And that's what we'll start to do in the next chapter. But the total drop got to be 100 feet. And so this change in voltage has to be the same as that. If I then divide both sides by time, what would you call this? And what would you call this? Yeah, this would be energy per time, power. This would be charge per time, which is current. And so the last piece of our puzzle here is to say how much power is being delivered to this light bulb. It is a combination of how much current and how much voltage, the two together. If we tie that together with Ohm's law, in place of current, we could put V over R. And so another way of calculating the power would be this. We could also use Ohm's law to replace V, which then we would get I squared R. And so that would be a third option we have to calculate the power. But we can either do current and voltage, or voltage and resistance, or current and resistance. And for this setup, it's probably best for me, since I can easily see the voltage, and I measured the resistance to be 60, to use this one and say I've got 8 volts, and I square it, and I divide it by 60 ohms of resistance when it is hot. The numbers become 64 over 60. And it looks like we're going to get a little over 1 watt for our light bulb here today. But what are the units? And that's why I wanted to close with this. What do I get in the numerator? Okay, I got volts squared, good. What do I get in the denominator? Ohms. And so let's pause for a moment and look at ohms a little carefully here. Kind of ran out of room here, so maybe I'll jump up here. But if I write Ohm's law in the way you're probably used to seeing it, and then rearrange it this way, the units for resistance are ohms. What are the units then equal to? Volts over amp. So I will take my 64 over 60 and leave it alone. Again, just a number greater than 1. That's not the interesting part. But then I would have voltage squared divided by voltage over amp. Now, of course, that would be voltage canceling with voltage. Okay, so that would be 64 over 60 volts times amp, right? Now, isn't volt times amp what I would have got if I had done it this way? Okay, so not a surprise that if I do it this way, I end up with that. Okay, but again, what does this come out to be? It does come out to be watts. What was a joule? I'm sorry. What was a volt? Joule per coulomb. Here's a new one. What's an amp? Coulomb per second. What happens to the coulombs? And so finally, what do I get? Joule per second is called a watt. Exactly. So not a surprise that I will get the power measured in watts, as I should. But I thought it was a good opportunity to show you a calculation with the units, because for some of you, this is all new units to you. But they do work out. And so just like you learned back in chapter 1, that a day was coming where we would do units you've never seen before, that's okay. They do work. Follow the same rules of mathematics for your units as you do for your numbers. They work. All right. Well, good luck on the homework. We'll do some examples on Tuesday.